welcome. Welcome particularly to all of the attendees of the Advances in Architectural Geometry Conference, which has skipped the rails from its usual European location to come and join us here in Cambridge this week, along with all the other members of our community who are here for the 14th Annual Edward and Mary Allen Lecture in Structural Design. My colleague and organizer of the conference, Caitlin Mueller, will step up to the podium in a moment to talk about the intellectual ambitions and history of the Allen Lecture, which is really one of the most remarkable events in the season of our lectures here in the department, and always a huge favorite of mine. I want to just recognize on behalf of the department and thank, first of all, the generosity of the conference organizers and the building technology group for organizing and presenting the lecture, but step back in a moment to recognize a kind of chain of generosity that goes back through the history of this lecture to Ed Allen's contributions to the department, to Ed and Mary's contributions to this community and to create this lecture, and then to the generosity that they've inspired in their own mentees and students, including not least Roger Goldstein, who's here with us tonight, whose family has recently chosen to endow and support a series of climate studios that advance the work and example set by another important donor to the department, Alan Spoon, and of course by Caitlin and Sheila Kennedy in advancing the first of our climate and research studios over the last 3 years. So this is really a remarkable and a beautiful community of giving and sharing and of thinking how advances in building technology, structural design, and yes, geometry as well, really support the making and doing of important and impactful work in the world at a time when we are incredibly conscious of the impact of architecture on all components of the environment, and here are engaged together at MIT and with our colleagues from around the world here tonight in very important and impactful work on behalf of architecture's role in the world. So with that, I would like to thank and welcome Caitlin to the stage to talk about the Allen Lecture, and we'll take it from there.
Hi, everyone. I'm so happy that all of you made it. Welcome to those of you coming from MIT, from the Department of Architecture, from AAG, to everyone else who came to this wonderful public lecture that we're able to have. Before we introduce our amazing speaker tonight, I just wanted to say a little bit more about the Edward and Mary Allen Lecture in Structural Design, which we believe this is the 14th instance of. We are so fortunate since 2012 to have been able to bring absolutely incredible structural designers and innovators to our campus to share their work, to spark ideas, to interact with our faculty and students, and to create lasting connections. I just wanted to read the list of the previous speakers because it's really exciting, and hopefully many of you have been at a lot of our previous events as well. Not in exact order, we've had Jörg Schleich, Bill Baker, Simone Velez, Mark West, Janet Eckelman, Mitsuru Sasaki, Les Robertson and Satine C., Guy Nordenson, Kate Siminen, Jörg Kanzet, Sigrid Adriansens, and Philippe Bloch. So an incredible list, and we are adding another one tonight with a delightful lecture by Lucas Epp. This lecture series is about structural design, yes, that's our convening theme, but it's also about broader ideas that connect to architecture, to the built environment, to the climate crisis, to emerging opportunities with technology. And we're really excited to bring that not only to the world of engineering, but also to the world of architecture, and bring these two disciplines a little bit closer together through this shared experience that we get to bring to our campus every year. And I think we've already seen the fruit of that, and we're incredibly grateful to the gift from Edward and Mary Allen, who not only gave us the gift to allow us to do this lecture, but also have really sparked a revolution in structural design thinking and education through Ed's amazing research and books that I'm sure all of you are familiar with. So with that, I want to thank you one more time for coming, and I'm really delighted to introduce my colleague and co-organizer of the AAG 2025 conference, Jonathan Rabagliotti, who will introduce tonight's speaker, Lucas Epp.
So thank you. So I first met Lucas when we were both working in London, myself at Foster & Partners and him at Bureau Happold. And we quickly found an affinity and a shared desire for advancing geometry, workflow innovation, and rethinking approaches. I've always admired the work of structure craft, beautiful details, focused on timber, but also elegant metal details, combining carpenter's craft, computational innovation, and advanced engineering. The structure craft has brought together engineering and construction, and Lucas has been at the heart of bridging those domains, the integration of data flows, design iteration, enabling computation from geometry analysis, logistics, pricing, quantities, and computation, putting the C, the computer numerical control, the C into CNC, to the point of generating G codes. And one of the key things for me is having a workshop to allow prototyping, to test hunches, and to experiment. And at the heart of this is thought and geometry. And so we're delighted to welcome Lucas Epp. Thank you.
All right, you guys hear me all right? Honored to be here tonight. And tonight I hope to talk to you in the spirit of Ed Allen, who, as I understand, I never met him, but through reading about his work, he loved the details. He took joy in details. And so today I'm going to talk to you about some of our work and some of our engineering philosophy in reconnecting engineering and construction. First, I need to start with a picture of my dad. My dad founded Structurecraft 27 years ago and has been a continual source of inspiration, not only to me, but to hundreds of other engineers who have watched how he's remerged engineering and construction at our company, Structurecraft. And John Oxendorf pointed out to me that we've got the free damped oscillation equations up here on the chalkboard. And so, of course, I had to start with this particular structure that my dad engineered. This is a footbridge in Banff, Alberta, Canada. And you might be able to see these little things right here and here. These are tuned mass dampers. And so these dampers are suspended on cables that are calibrated, the flexibility of those cables to basically damp the walking and jogging frequencies of this bridge. And he went on to do that with another bridge, which is a shallow compression arch also in the town of Banff. So I'm a structural engineer, but my career started perhaps atypically. Being surrounded by carpenters, I was pushing the broom on the shop floor. I was cutting wood. I was seeing carpenters build structures, but I was also watching my dad at the dinner table coming up with structural ideas. And so that kind of led me perhaps to think differently than many engineers might. Our company, we're both engineers and builders, and we work across North America and Asia on all types of structures, from long span arenas to office buildings to institutional. We cover the range of structure types. And perhaps what's most unique about our company is the number of different professions that are represented inside our organization. MIT, I learned, such a multidisciplinary focus here, and it was inspiring. And in our company, we have almost 200 structural engineers, computational designers, carpenters, master carpenters, installers, project managers, people who can model, and software engineers. And so today I want to talk about design and construction and why have they separated, and why we strongly believe we must bring them back together. It's not that they're entirely separated, but in many of the buildings that we build in the built environment, there is a bit of a separation which is formed. And so going back to perhaps the first Allen lecture, this is Jörg Schleich, and he wrote, "Care and detail thinking and tinkering no longer pay off because labor cost outweighs material cost. So that soulless, clumsy structures are cheaper than those lovingly conceived. And isn't that true? But it's perhaps beyond just the increased cost of labor. I believe it goes to the interfaces that we have between us as designers and us as builders. And right from the start of my career, I saw how interfaces shape what we design. From Bjarke Engel's comic book sketches, which perhaps changed even building owners' perception of why their buildings exist, to the rise of grasshopper and parametric design, and seeing that in my early years in London, how that shaped how we could design different shaped buildings. And as a structural engineer, of course, the interface of the software, wrestling against analysis, convergence and instabilities, and spending more time, I remember as a graduate engineer, perhaps myopically focused on the interface, the software, than on the structure I was designing. And then seeing my father working across these structures and connecting engineers and carpenters to create incredible structures. So today I want to talk about some of these interfaces. So if we go back 6,000 years ago to Mesopotamia, we shaped raw earth with our hands. We created these mud bricks dried in the sun, and we built these tholoi, these monoliths, these houses that were a direct kind of human material interface. There's zero barrier between design and construction. And as we built these, we learned from our designs and from our construction because we lived with the consequences of our design choices. We learned by doing. We had an intimate knowledge of our building materials. The next interface that started to rise was the drawing. 5,000 years ago, we were using reed styluses to etch on clay tablets. And all of a sudden, there was this possibility that the mind conceiving was perhaps different from the mind that was creating. The Greek word architecton, which literally translates chief builder, was responsible for both design and construction. And it wasn't until the Renaissance that we saw more of a separation between the designer and the builder. Then we had, after this interface of the drawing, we had this idea of a module. From the earliest cities, we started to establish ways of partitioning space into kind of repeatable geometries, modules that spread across geography and across culture. But these modules, weren't just a physical object. So the Roman modular brick or the Greek column, they were, in a lot of ways, a shared understanding, which allowed construction knowledge to spread. But once these modules were entrenched in our industry, these industry-accepted modules perhaps became more expensive and difficult to move away from. They gave us a structural design language, but in doing so, they shaped what we say. The next interface, I believe, that between us as structural engineers and our buildings, it was really the rise of the calculation. During the Enlightenment, scientific method, and mathematics, we applied it to construction, and now all of a sudden, we could move beyond just guild tradition to predicting material behavior. Our design knowledge became codified into building codes and standards, and this enabled, safe construction across more complex structures. But as these standards developed, they also started to become constraints. As engineers, we began perhaps designing for code compliance more than just for structural efficiency. The next interface was I call the catalog. During the Industrial Revolution, this plethora of materials that started to hit us as a construction society. Manufacturing comes from the Latin word manufacere, which literally translates made by hand. But that became mass-produced, didn't it? As designers, there's the possibility of being limited by not what we could craft, but by the supply chain. For some, the catalog became maybe perhaps a boundary of imagination, and sometimes we end up navigating the market more than deeply interrogating materiality. The next interface that arose really 1963 right here at MIT was the computer. And this is Ivan Sutherland's Sketchpad, 1963, where he created the first CAD software and using a stylus to direct interface with a computer for the first time. And this computer, of greatly improved what we could do, both from a coordination standpoint, complexity, simulation, and it was the first digital interface. This digital interface is different than an analog interface, as you all know. So the hand-drawn line, it's got thickness, it's got texture, it's got an inherent ambiguity. It invites a conversation, but a digital line is mathematically precise and perfect and absolute. And perhaps we started to think that because we could model something, we could build it. I run a sketching class for our engineers, and we put a hunk of CLT down on the table and a sheet of paper, and each person gets a pen and draws the CLT block. And then I put up a drawing of a Bluebeam sketch of that same CLT block, and it's red lines, right? Every engineer would draw that CLT block in Bluebeam the same. But the sketches we get back are 40 different, highly varying, looking at grain, looking at knots, looking at cracks. So analog versus digital. And now, of course, we face a new interface, artificial intelligence. And for the first time, our tool is not passive, it talks back. We now have this vast knowledge and power at our fingertips. But with this incredible power, I believe, also comes an incredible responsibility. I think the danger is not that the machine will take over our designs, but that we may passively start to accept the optimizations without understanding the first principles that govern them. So I think these AI tools that we build as an industry over the next 10 years will have a huge impact on how future generations think about design. So these 6 interfaces, from drawing to algorithm, they've enabled these incredible new scale, forms, and complexity in our built environment. And they've also enabled collaboration, this idea that we used to spend 10 to 20 years working on a single building, and we now spend maybe 1 to 2 years working on many buildings at once. And so these interfaces have enabled us to collaborate across disciplines and achieve more complex and more varied geometries and forms. But we also have constructed this wall between design and construction. I call it the construction contract, right? And we lob change orders and RFIs over that wall. And so us as a practice, we ask, how do we reconnect design and manufacturing and construction? And so today I'm going to talk through a series of projects looking at using timber as a natural material and how we've used that to kind of perhaps challenge or extend some of these interfaces. Has anyone heard of a peeler core? Raise your hands if you have. A few. So you take a log and you chop it up with a bandsaw, right? And then you take those boards and you agglomerate them into glue laminated timber, cross laminated timber, et cetera. But actually there's another way to process a log, and this is how plywood is made. And so a log goes onto a lathe and it's peeled. And at the center of that log is a peeler core. And these peeler cores are produced by the billions each year by our industries worldwide. They're juvenile wood, the youngest wood in the tree. They check. They're naturally, in some ways, not very strong. And so one of our earliest projects, led by my father, was a tetrahedral space truss, conceived using these peeler cores as the structural elements. And so, as a traditional engineer, we may have barriers to using a product like this. There are no accepted design values. How about this checking and the cracking that occurs? How can I get happy with the structural performance? How am I even going to buy enough of them? And this engineer-builder approach really goes and says, well, I'm going to take the responsibility. I'm going to actually deeply understand this material. I'm going to go test this material and really understand it, and then take responsibility for executing the construction. So here you see these peeler cores with these custom engineered steel rings which have been inserted into the ends to restrain the checking. And then casting, which allows each of these peeler cores to be connected one to the other. And then these bands, different colors that actually represent different structural capacities. Space frame is a highly redundant structure, and so if there is one defect, well, it doesn't matter because you have redundancy. And so this idea of using a waste material to create a two-way spanning timber space truss. The second project I want to tell you about is the speed skating oval for the Olympics in Vancouver in 2010. The humble 2x4 reimagined as a structural composite panel. And so you see these big glulam arches that are spanning about 100 meters across this oval. In between them is a series of these so-called wood wave panels. And this was my dad's first sketch of this, this idea of taking 2x4s, staggering them up and down, and then tying them with a cable at the bottom to basically force arching action through the 2x4s. So this is a 45-foot clear span. Normally, if you took a 3.5-inch thick mass timber panel, I mean, you might be able to clear span 10 or 12 feet. Here, with an effective depth of much deeper, because we're tying this arch, now all of a sudden we can clear span 45 feet, but with only 3.5 inches thick of structural material. And so back to this connection of the engineer and the builder, here we are in our shop designing equipment and machinery for how to actually manufacture these wood wave panels, how to invent the hydraulic press that would press them into shape, how to prefabricate these strands of lumber that connect and create this arching action up to the plywood shell on top. But then, of course, how to predict the load capacity of a structure so unique. We, of course, had to load test it. So here we are in our shop conducting snap-through buckling tests of these wood wave panels. And so creating a deep understanding of materiality and how the construction and manufacturing process impacts what we design as engineers. And some pictures of this structure during construction and this pattern of the blocking, which actually created an acoustic absorptive surface, which actually reduced the reverberation time in this giant speed skating oval. The next project I want to talk to you about is a project in China, and I want to talk about the interface of the computer. This is a series of domes. Every single piece of timber in these 3 domes is unique. They have almost a clamshell radiating pattern. And so the computer really is the only thing that enabled us to handle the 10,000 or so unique pieces in this project. But we also had fabrication constraints. And so this glulam was going from Europe to China on rail. And so we had this constraint of the shipping container. But we were also cladding it with glass. And so we had this constraint of doubly curved glass. How big of a glass piece could we get? And how does that influence our structural size? And so here's a pragmatic, perhaps, approach way to create doubly curved glulam. We take a singly curved billet, and we actually mill out this very slight double curve to create doubly curved glulam without being limited to only one of a couple of manufacturers who can do that natively. And so here's these prefabricated panels, which are highly influenced by this shipping container in terms of their size, with joints that are influenced by how we're going to build it and how we're going to assemble the structures together. These 3 domes are biodomes, so desert dome, aquatic dome, all sorts of different environments inside the domes. And the smallest 2, we were able to create this 2-way grid shell without triangulation from a structural standpoint. And in order to do that, we needed to prove the structural capacity, the torsional capacity of the joint between the 2 directions. And we actually created this joint using only screws. And so this is, again, structural testing, looking at the shear capacity and also the torsion capacity of these connections that we had designed. But for the largest dome, we had a grid of cables to triangulate the structure. The span was too big. We couldn't restrain this kind of in-plane shear buckling. And so we had to come up with a grid of cables, constantly changing angles that the cables intersect with, and how to connect those cables back to the timber grid shell above. And so here's this concept of rotationally decoupled castings, which thread onto a central threaded rod. And those castings not only allow the cables, or sorry, that threaded rod not only allow the cables to thread on, but they allow us to actually draw that cable system closer to the grid shell above. And so here you see these stainless steel castings. And this was one of our first major projects in China. And as we started to talk about how to build this, I was thinking shoring towers. And the local engineer said, no, we're going to scaffold the whole thing. I thought that was bonkers. How can that be the most cost-effective way to build these domes? But as I later learned from the folks at Grimshaw, that's also how the Eden domes were built, fully scaffolded. And no, this is not bamboo scaffolding. This is metal scaffolding. But construction approaches in China are quite different from what we might be used to here in North America. We had people riding the panels up onto the dome, if you can imagine. But here you start to see these grid shells take shape, and and this kind of idea that you could create a non-triangulated grid shell only using screws, so there's no metal plates between these two directions of timber. And so when constructed, this was, I think one of the largest clear span timber grid shells of its type in the world. So the next project I want to talk through talks a little bit about the interface of kind of the calculation. This is a project where we're using glulam, but we're using it as a hybrid with steel to create a triangular truss. So we have a double top chord and then two glulam bottom chords connected with steel webbing. This is in Tianfu in China, and this is about a 750,000 square foot project. And these vaults clear span up to 400 feet and are up to 150 foot tall. So as tall as a 12-story building at their tallest. And here, if you think of a vault, of course, compression structure, catenary shapes, as we looked at earlier, are the most efficient way to do it. But timber alone for an arch of this span would be a challenge. And so we're starting to think about hybridizing and creating structural depth again with steel trussing. And looking at the analysis of a pin-based arch versus a fixed base arch, we start to realize that if you fix the bases, you get a natural kind of hinge point at the mid-span. And that allows us to start shaping that truss from deep at the perimeter to shallower at the edges. But it also informs some of the thinking around how we connect the top and bottom chords, this idea of almost a Vierendeel connection. And so the trussing in this truss, it doesn't node out, which it should, of course, because the trussing should node out, otherwise you get bending moments and shears in that bottom chord. But here what we're doing is, by not making the steel node out, we've actually created a way of splicing and prefabricating this truss. This entire project was built during COVID. We were only able to get one person into China. It was on lockdown. And so we had to create almost an instruction set to allow the local crews and instruct them how to actually build this structure when we couldn't go have the normal crews we would have there to help guide in the whole process. And so here you see almost this 3D IKEA set diagram connecting the top and bottom chords into these sub-assemblies, which then get, and that's done off-site, which then get craned onto the job site and connected into larger lift assemblies. These lift assemblies then get craned up onto shoring towers, so I finally got to use my shoring towers. And we built them over top of structures that were actually being steel and concrete structures that were being built underneath the arches at the same time. And so the installation technique actually greatly informed the structural system. Oops. So here you can start to see one of these lift assemblies being craned into place, and some of the shots from during construction. I think there were up to 10 or 15 tower cranes and mobile cranes going at one time on this project, and it was actually constructed in 8 months, which is an unbelievable achievement for a project of this size and scale. So next project I want to talk to you is, again, looking at the use of the 2x4 as a structural material, but instead of staggering it up and down, here we're making a flat mass timber panel, and we're actually curving it. So this is for an aerospace museum in British Columbia, where I'm from. And so the roof of this aerospace museum is about a 60-foot clear span. And this concept, again, using trussing, is taking a flat panel, curving it, and then using that curve to create structural depth because we're post-tensioning it against a cable below. But when we curve that panel, of course, we're locking in stress into the timber panel. And so that could be of concern because we're actually putting a lot of stress into this timber panel. It's actually close to breaking when you do the calcs. But timber is a very interesting material. It creeps, and it actually gives way and yields over time. And so those stresses that may have existed initially eventually dissipate over time. And here in the workshop, testing the curvature of these panels and then prefabricating them just off the job site and flying them into place on the structure on site. So you get this kind of rhythm of 4-foot wide trusses that march down the space. And you've got, again, 3.5 inches of material achieving a 60-foot clear span. This project with Michael Green, this is, if built, will be the tallest all wood building in a seismic zone, I think worldwide as far as we know. And so this is in Vancouver. And this is really the challenging the interface of the calculation. As engineers in a seismic zone, we have pre-approved systems, concrete shear walls, steel brace frames, or BRBs, right? But if we want to use wood, well, there's no real pre-approved systems for how to get to a 12-story tower in a high seismic zone. And so this is working with some of our engineers who did their PhD at the University of Canterbury in New Zealand, and looking at creating steel link beams that connect CLT shear walls to actually yield and create a fuse in an earthquake. And so these are replaceable steel components. And so this is some of the testing that happened at the University of Canterbury, and we are actually just in the process of repeating at Oregon State University, where we're looking at how these coupled CLT shear walls can create energy dissipation and this kind of ductile hinge, almost like bending a paper clip back and forth during an earthquake. And next, this interface of I want to talk about is really the physical model. So it's kind of a subset of how we calculate as engineers doing physical modeling. This is a timber grid shell in Atlanta this is actually for the FIFA World Cup viewings. And so we're in active design and construction on this right now. And this Pringle shape, of course, has been done many different times in quite a few different materials. But here we're perhaps doing it maybe for the first time all out of timber. So it's a doubly curved glulam ring beam, and then a bending active grid shell, which is draped onto this ring beam. But as we're starting to think about the geometry for this structure, what surface should we choose? We could obviously define this surface in many different ways, as a hypar, as a catenoid, or as actually Chris Williams pointed out to us, as a surface of constant negative Gaussian curvature, which has a very interesting geometric property that you can form Chebyshev nets that actually basically are deployable. And so and we can do that without really doing anything other than minor axis bending and torsion in our timber elements. We don't want to put major axis bending into these grid shell elements. And so as we're starting to look at kind of which grids to choose, we're comparing not only structural efficiency, but also buildability, importantly, buildability. And so this idea that this grid, this Chebyshev grid, could actually, sorry. One second. Frozen. Sorry about that. Okay, here we go. Hopefully we're back. So this idea that this grid shell could actually be built from flat, and starting to simulate what that might look like. And so if we lift it from certain lifting points on a crane, that's not working, but what shape will it take, and will that shape be a close approximation to the ring beam that we have around it? And actually, just yesterday, this is hot off the press, we just finished a 1:10 scale model of this grid shell. And so we're literally simulating exactly how we're going to lift this grid shell from the ground into place, and starting to understand kind of at a much deeper level of materiality how some of these connections that we're coming up with for how do we connect the grid shell elements to the perimeter ring beam might affect how we're going to actually build it out on site. Because as you can imagine, this is somewhat cost effective to do in a shop, but you go out on site and this thing is hanging on a big crane. You do not want that thing hanging overnight, right? You got to do this in one day, and you get one shot. And so simulating it and doing physical modeling to really understand how it's going to perform is incredibly important. On this project, we also had the opportunity to compare CFD and wind tunnels, something that I'd worked on in London 15 years ago. And I wanted to see how is the state of the art advanced? Can we now replace the wind tunnel with CFD? And here we're working with a company called Aerosim, and we're actually conducting a very detailed CFD analysis, detailed enough to actually get the structural pressures out of. And so an incredibly accurate simulation, but as you can see, as the vortices kind of shed off of the leading edge of this structure, the key question is when does the wind kind of reattach itself to the structure? after it's kind of being lifted off. And so going into the wind tunnel, measuring all the pressure coefficients from the wind tunnel, and then remapping and comparing the wind tunnel with the CFD, what we realized is overall, like the total net forces on the structure were actually quite similar. But the way they were distributed was slightly different. And that phenomenon of how the vortex shedding works in a lot of detail was actually just different enough that it actually significantly changed the forces and results between the wind tunnel and the CFD. So we used the wind tunnel results at the end of the day to design the structure. And now I want to talk about something that we've been investigating as a practice for the last few years, really actually since the start of our practice, is timber joinery. Something, if you think about timber structures as old structures, we didn't used to have metal plates or epoxy rods or screws to connect them, did we? And you know, often we're inspired, this is Brunel's Lost Bridge in Paddington, inspired by engineers and builders who shaped material in their rawest forms, Candela with concrete, or Dieste with brick, or Friato with tension and timber grid shell structures. And so we're starting to think about, well, joinery, transferring structural forces for modern buildings. How do we do that? So this is a project at the University of Kansas with Bjarke Engel's group. And this is the new School of Architecture and Design. And so it's a building that's meant to house a teaching environment for students for generations to come. And Big posed this as a teaching tool itself. This building is a teaching tool. And so how do we turn this building structure into a teaching tool? We have the systems on display. We're not using any drywall in the structure. We're actually replacing rock wool and the external skin with hemp insulation. And so turning to the structure, well, what do we do with the structure? How do we make this timber structure something that inspires students of the future? And so here we're starting to look at different kind of joint topologies. And I was on a call with Bjarke, and he challenged me. He said, you know, I asked him, what do you want for the joints? And he said, no, what do you want for the joints? And so I had to start thinking, well, what do I want to do for these joints? And so I started sketching all of the steel plates and hardware that would normally be in a joint like this, and suddenly thought, well, what if we could go back to how we used to connect timber, just wood to wood? And so this is kind of a first sketch of using geometry to actually inform how the structural forces flow in this diagrid. And because we have a workshop, then a few weeks later, we're down there with some of our master carpenters prototyping this joint and starting to see, could our ideas work? You know, could we use geometry of how we mill these timber pieces to actually lock them together, hold them in place, and transfer structural loads? And obviously, this is something that it perhaps hasn't been done before on this scale. Oops. Some of these videos are not working. My apologies. Well, we'll just keep moving. Hasn't been done before on this scale. And so we're thinking about, well, how do we actually prove this out? So we actually decided to make a full-scale mock-up of one corner of this building. But first we had to decide, well, what was this diagrid going to be anyways? And so here we're looking at which diagonals should we keep, which should we drop? You know, do we do some topology optimization or follow the principal stress lines? But we landed perhaps with the simplest is the best. And of course, you know, a big X is the most structurally optimal way to brace a building of this kind. And so that's what we ended up with. And here's some pictures of the full-scale mock-up we built, and just some close-ups of the joinery that we started to create. And you know, a lot of people think, well, this was just a CNC machine. Actually, the CNC machine only did a part of this, and then actually the finishing bit was done by hand by master carpenters. And we actually calculated out it was going to be cheaper to do it by hand because it's going to take less time than it would be to run on the machine to get every joint perfectly square. And so the art of craftsmanship is not lost. It appears that all my videos may now be not working, which may be a problem. We'll see. So moving on to another project where we're using mass plywood, MPP, mass plywood panels, which are basically cross-laminated plywood or basically LVL. This is for a project in Barbados, the new National Performing Arts Center with Adjay Associates. And we got given somewhat of an incredible task. We got asked in January of this year, could we build the structure and have it complete by August? And we hadn't even started design. I mean, no, right? It's impossible. But working with the architect and the owner, we started to peel back the structure to kind of the bare bones. And we started to realize that, hey, maybe if we turn this into a temporary part 1 or phase 1, we could actually build it in that short amount of time. And part of the structure is, of course, it's a big auditorium, but we have a performing arts center with a stage, and over that stage is a giant truss. And so this truss had to be about 23, 25 feet deep to conceal all the equipment behind it. So we started to ask ourselves, well, could we use this truss as a way to actually explore joinery? We had a very limited amount of time to procure materials, so actually if we could do all of the fabrication in-house and not have to procure steel from a steel shop, that would reduce time. And so here we are sketching connection ideas with our carpenters and starting to look at what truss typologies might be the right truss typologies. And so, perhaps the most obvious one would be to put 2 big beams and connect them with verticals, or just do a how truss, but then you end up with tension. And how do you take tension in an all-wood joint? That's quite a challenge. And so we ended up with this kind of arch where we're almost trying to transfer most of the loads in compression. And so this truss that kind of emerged is somewhat of a structural optimization problem. What is the optimal arrangement of these diagonals? And how does the bending forces and the axial forces, how do they change as we change the distribution or the angles of these trussing elements? But it's also a manufacturing and a connection detailing problem. If we do a pure genetic algorithm approach to determine what the structural optimal solution is, we will get a geometry. The question, of course, is that geometry buildable? And so the geometry that resulted of the optimization, it had splice joints in the wrong spot. It had connections too close to the ends of some of our elements. And so what we ended up doing was we actually changed the geometry to respect the manufacturing and construction constraints. And those central pieces, what you just saw is this is a hurricane region, so we actually have net uplift on this truss. So the central 4 pieces are actually acting like a mini truss when we have load reversal. So as we're starting to look at connection typologies for these all-wood joints, of course inspired by some of the Japanese joinery of millennia ago. This is the Okaki Daisen Sugi joint, and then also starting to invent some of our own connection types, these kind of mass plywood tenons, or these kind of notched compression joints that transfer, this particular joint transfers up to 230,000 pounds of compression from this brace down into the bottom chord of the truss. And then about 4 weeks later, maybe 6 weeks later, after designing this truss, we're down in our shop actually manufacturing the truss, test fitting it, chiseling it, working with the raw material and shaping it by hand, a lot of it. This entire truss was manufactured in the space of around 2 weeks, which is kind of an incredible achievement. It won't fit. We used amaranth, which is a purple heartwood, for some of the dowel joinery. And here you see our whole shop crew gathered inside the truss. And then the next challenge for us is, okay, we can design it, we can manufacture it. How do we ship it to Barbados from Vancouver, Canada? And how are we going to get it there in time? We were going to fly it in 2 747 cargo jets. That was our original plan, because that's literally all the time we had. And then we realized that Bridgetown Airport cannot unload a 747 cargo jet. They don't have scissor lifts tall enough to kind of yank the stuff out of the plane. And so plan B, ocean freight. So we actually chartered an entire vessel, drove overnight from Vancouver down to Houston, loaded that vessel, and shipped it over to Barbados. Here you see some of the process of rebuilding that truss out on the job site. And this is a complicated piece of joinery. And so one of the things that really helped was our incredible craftsmen who were part of building the truss the first time in our shop, some of those same people went out to our job site out in Barbados and helped put that truss together a second time. Of course, some editing required, moisture content changes, humidity, wood swells as it gets wet, but actually, all in all, it fit incredibly well. And so here you see it, an all-wood truss spanning the first national stage for Barbados. And maybe one of the most incredible things is we did finish it on time. So I'll show you the time lapse. But this was another interesting use of wood joinery. In modern mass timber construction, we like to use these pre-engineered metal hangers, Rikon or Meganite type connections. And so on the left-hand side, you see what we created, which was this MPP kind of dovetail tenon, which actually allows us to do the same thing, but using wood instead of metal. And so here you see that flying into place, or not, if the video doesn't work. And here you see kind of a time lapse of this structure being built. The entire timber superstructure was built in the space of just about 3.5 weeks, which is an incredible achievement and a testament to a lot of very committed people. So here you see some of the photos of the structure during use, and the lateral force resisting system for this structure is actually quite interesting. We used cables, and actually only one side of the structure is working under wind from either direction. So we have a fairly small lever arm, but these cables anchor down into the concrete slab, and when you actually look at the structure, they almost disappear. So it almost looks a little bit like a mechanism, the structure. And so that's some thoughts around how we might shape timber joinery. And to close off this lecture, I want to talk about software and this new AI interface I talked about earlier. Branch is a piece of software that we've been starting to work on internally over the last 3 years. We measured our digital footprint, and we have so many different pieces of software in use to go all the way from design to construction. I think more than 30. And so all these different packages, there's information barriers, you guys all know, right? It's hard to get data in and out of different softwares. And so we started just by thinking about, well, hey, could we actually replace the detailing tool we used? And so this is branch detailing, which runs on top of Rhino, this particular version, and allowed us to go all the way from detailing and modeling through to creating the CNC files and the G code for all these mass timber projects and steel projects. And over the last 3 years, Branch has pumped out almost 2 million square feet of built projects. And this is just a sampling of all the shop drawings that have been created out of Branch. So all sorts of different types and shapes and sizes and everything from timber to steel to cross-laminated timber, the glue lam. These are some of the shop drawings from the project in Barbados that we just looked at. But now we've started looking at what about a vertically connected platform that allows us to go from conceptual design into detailing all the way from the start to the finish. And so what you're seeing here is a conceptual design platform. This is actually freely available. Anyone who wants to use this can. It's on the web. If you go to branch3d.com, you can go just try it out. And you can go push and pull on your structure and see how your material efficiency changes or how your carbon changes. And you have a kind of almost a smart structural framing algorithm, which allows you to kind of explore different building massings and column grids and densities more rapidly than you may have been able to in the past. And so this has actually got a real-time analysis algorithm working in behind it. And so one of the goals is on every project like this that we investigate, we have to compare materials. We have to compare timber and steel and concrete, and we have to compare material efficiency, carbon, all these things. And so this allows us to start exploring those more rapidly. And it also allows us to gives us kind of a deep insight into the product landscape, and so all the different mass timber manufacturers and CLT panel widths and all that kind of thing. But now we're starting to think about, well, how is AI, or how should AI influence the software we design? I think AI is an incredibly powerful tool. It needs to act on our behalf, not act for us. And so it needs to be something that we remain in entire control of. And so one of the things that we've been thinking about is, can we deploy AI as a toolsmith? rather than as something that is doing our job for us? Can it be something that helps us create tools much more rapidly than we used to in the past? And so we've seen this kind of progression of artificial intelligence from classic kind of rule-based through to foundation models. And each of them have incredible value for us and some limitations. And when I talk to my structural engineers about AI, they're like, I can't trust AI. It's probabilistic, it's not deterministic. How am I going to be able to trust the result? And of course, with some of the reasoning models, we've seen big advances. But I think one of the things that we need to start doing as an industry is start creating foundation models that can reason about deterministically correct things. And so this is just a little prototype, which is now not going to work. There we go. So imagine you have a structure like this, and you're trying to understand how the structural system works, how the forces flow. And imagine what chatting with your model could look like, not to design your structure for you, but to create interfaces that change how you interface with your structure. And so I think this is perhaps the next foray that we need to do as an industry is start investigating how our tools can become smarter, can become truly computer-aided design tools, and start to give us a smarter way of interfacing with our models, because we do now have an incredible power at our fingertips. This is the concept of exploring similarity of bending moment or shear curves across a building, and starting plotting kind of statistical distribution of those across your structure, and then being able to kind of interface and kind of filter your structure down to the beams or the structural elements which are the most similar to the one that you may be currently designing. And so for those software engineers in the room, this idea that in blue we have pieces of code that we know are correct. As structural engineers, we can independently verify it's doing the right thing. But AI now starts to reason around these verifiably correct things and construct them in ways and patterns and at speeds that we as humans never could have in the past. So I'm really excited by where I think this is going to go over the next 10 years, but it's really important that we take control of how these tools are going to shape how we design buildings. And so to close, I just want to say a few things, just like Ed Allen, I'm sure would have said, is take joy in the details. And so to all of you here from AAG, master the digital interfaces, but stay deeply connected to materials and how they perform, and be the architect on that chief builder. Thank you.
Wow, that was absolutely incredible. I am sure that Ed would have absolutely loved that. We have time for a few questions, and I'll just stand here with Lucas so I can repeat the questions, but if you'd like to ask a question, it's easiest if you come down to one of the microphones. Yeah, please. Can you just go to the micro, or I can repeat your question. Go ahead, I can just repeat it.
Okay. Hi, thank you so much for the presentation. It's very fascinating. And I'm especially curious about the structure of the fully timber, structure that is fully connected through woven joint. And the first thing comes in my mind with this kind of structure is those Japanese temples that has been existing for thousands of years. And I feel like one thing that's really fascinating is that the fact that this kind of fully wooden joint system, when one timber is broken, it can be replaced by another so that the building can last for thousands of years. And I wonder if that's the same for the structure you designed, and have you ever considered this as a property when you design? Thank you.
Well, that is the interesting thing about using timber joinery, isn't it? It's not gluing it together, so you can actually go take that same structure back apart. Of course, we put a lot of things around our structures today, so getting to that structure may be a challenge. But I think inherently, yes, it's replaceable. You may need some shoring, but yeah, you could take it apart and put a new piece in its place for sure.
Thanks so much.
Other questions?
Thank you so much for that lecture. It was truly inspiring. One of the things that strikes me the most as a business owner myself, working in fabrication, is the confidence you have to take all those risks one after the other. And with the crescendo you built with the presentation, like each time building your own springboard and jumping without looking back every time. Like, do you have any vertigo? How do you feel dizziness? Like, how do you build such confidence to go through?
I mean, I think us as an industry, we've become quite risk-averse, haven't we? If you look back to centuries ago, we had to take risks to build. We had no way of predicting whether our building was even going to stand. And so I would like to encourage each and every one of you to take more risks. I greatly dislike the litigious and risk-pushing society that we have sometimes become, because I think that these contracts and this idea of liability, has maybe made us more scared of our designs than we should be. So go break something, and maybe you'll find out that your structure is 10 times as strong as you thought it was.
Thank you.
Can I ask you? Yeah, just in the same way, you kind of mentioned about learning by doing. When you learn by doing, there's like a lot of failures, right? But when we curate a presentation, we don't show those failures. Like, is there some of those failures you would like to mention about? And what your learnings were from that?
Yeah. Well, yeah, of course, you have to learn by failure. And as structural engineers, we learned by failure through hundreds and thousands of years, didn't we? And we still learn by failing our structures and load testing our structures. That little scale model I showed you of the grid shell, we're planning to load that up, and we may even load test that full structure. We've load tested actually many of our structures. We had a structure that we designed. It was a mass timber office building, and they poured, I think, almost 4 inches too much concrete on the floors. There's a 2-inch concrete topping, and we ended up with 6 inches. So you can imagine the load on the system went up by a huge factor. And so, you need to shut down the building. Do we need to evacuate? What's going on? And so we actually went and took the joints that we had designed on that building, and we put them into our laboratory and actually tested them to failure to see, what the actual capacity was. And we actually had enough reserve to be okay. We had to do a little bit of reinforcing here and there, but not a holistic, carbon fiber reinforced side plates everywhere thing. So, and yes, we have had issues. I mean, you think about timber. Timber is a natural material. Its worst enemy is water and rot. And so anytime you have a timber structure that's potentially exposed to water, you have a potential problem. We had some structures where, leaks in envelopes, accumulate over time, and you start to see structural rot. And so those are big lessons learned. Be careful in how you're specifying your building envelope. Those types of lessons. But yes, lots of lessons along the way.
So I asked you this question earlier, and I'm back for the answer. Which of your buildings are you the most concerned about? Could you tell us a little bit about why?
On the spot, yeah. So I think, maybe picking up on what I just said, one of the structures we built in China had one of those leaks, let's just say. And so, yeah, that is concerning, because when timber is exposed to water, it's a problem. And so suffice to say, we had to go put in place measures fairly quickly to go remediate said issue. And so, yeah, sometimes, anytime you have those types of issues, you do need to be worried.
Professor Reinhardt.
Hi, Lucas. That was fantastic. I didn't know anything about structures, and I keep on learning from my colleagues, but this was deeply scary and impressive. So you talked about that, like at MIT, we always try to be multidisciplinary, and then obviously you live that in your company. And we have the luxury that we have students coming for 3-4 years, and then they maybe are architects or they're engineers, and then they have 3-4 years to learn. And here I see these folks in these videos that are, master crafters, master carpenters, software engineers. How do you build that up, and what do you think is the right mix between you got to know your stuff well, and how much of the other fields do you need to know? Is it a few people that have this broad view, or how do you organize that in your company?
That's a great question. I think we think a lot about that and how to actually broaden the horizons. I mean, it's a fairly recent thing, isn't it, that we've become specialized as disciplines. And so I think we really encourage our people at our company to think broader as generalists, to go across departments, to go work in other fields, go out into the shop, spend a few months as a carpenter, go out into the job site as an engineer, and actually live the life of having to build that structure rather than just a few site visits for the duration. So we definitely try to encourage that, but it's hard because, of course, specializations are even embedded in how we teach and the programs at our universities, and so they become self-selecting in some way. But definitely think it's very important, and I love the focus here at MIT to kind of think cross-disciplinary.
So timber is obviously like a good reaction to concrete and the environmental impacts of concrete, but it has its own impact of deforestation and ecological collapse when you clear cut a big forest. It seems like your company is very large and set up all over the world. Can you talk a little bit about sourcing the raw materials and forest management and these sorts of questions?
That's a big question. Forest management is a very important issue. And it's handled everywhere from very well to very poorly on an international scale. I would say we can learn lessons from those who have been doing forestry well for decades and centuries. And yeah, certainly clear cutting, if not managed properly, is not the way to go. But I would say that there are many forestry companies across the world that have been sustainably and successfully harvesting their forests now for well over 100 into 200 years. And of course beyond, but I'm talking in the kind of modern context. I look at Central Europe and the replanting and harvesting cycles they've invested in, and multi-generational approach to harvesting that they've invested in has paid dividends. And so, in North America, I think we do have some things to learn still in forestry management, but we also have some incredibly good well-managed forests here as well.
But it's not something that you guys.
We don't harvest wood ourselves. No.
Thank you.
Yes, Iman.
Oh, thank you. Thank you so much for this. It was fascinating and beautiful, poetic and technical. Covered the entire spectrum. I don't know if I have so much a question as much as I want to repeat something that you said that I thought was really important in the context, I think, of a lot of the conversations we're having in this conference, but I think a lot of the conversations that happen in school with students, particularly studying structure. You said something when you talked about the very first project with the peeler cores. You said that there's, with redundancy, you actually can minimize waste. And there's a really beautiful, I think, sort of paradox in that, obviously. It's a reason you mentioned it. And I guess maybe to frame it as a question, or if you might want to say something more about this as an engineer, but also someone who deeply cares about material, deeply cares about the climate, and craft. That what's your attitude towards optimization, in the way that we talk about it today? I know in many ways probably is so counter to the ways that you might think about things as an engineer. So I just thought that was a really, really beautiful point, and I would love to emphasize that to students in the room as well.
Yeah, redundant structures are not so common. Actually, most of the structures we build are really not that redundant. Even though we may try to make them redundant, but you have a big enough structural event, as it were, and your structure's coming down. And so, yeah, redundancy is a big topic, I think, in timber structures particularly because it's a brittle material. There is a lot of active research, including at ETH and other universities right now, into how we create more redundancy in multi-story timber structures. It's important. Yeah, I'll leave it at that.
Yeah, oh, please.
That was
Professor
great.
Oxendorf.
Thank you so much. I'm smiling for Ed Allen. He would have loved that. I just want to continue in a slightly technical way on the redundancy question because, as my poor students know, I'm deeply skeptical of linear elastic finite element models because as soon as you become indeterminate, let's take a four-legged wooden stool that you've all experienced in a restaurant or a cafe where you have an uneven surface by 1 millimeter and you get a totally different force distribution. So it only takes a few millimeters in the real world. We're building in a hostile environment and your models are completely off. And so you're always skeptical of your models, but can you just talk a little bit about how you think about this? Because the model is always wrong. It's a poor approximation. But are you ever going back and testing, and how far do you push that? You talked about experiment, but we live in a first linear elastic model, which is definitely wrong, but everyone believes it. So just how do you think about that?
It's a great question. The way we like to think about it is by taking a first principles approach. And what I mean by that is going outside your finite element linear elastic model into something where you can actually approximate your structure by hand. And truly visualizing how the forces are flowing in your structure. And by doing so, and by being able to visualize in your mind how a structure moves under load, you can start to visualize what would happen if I did X, Y, or Z, or if I moved that support, or if I deleted that particular structural element. And that that thought process leads you to understand where you may be most sensitive, or your structure may be most sensitive to an issue. And that should be the leading thought process for how you interrogate your model, or even how you build your model in the first place. At the end of the day, these finite element models are just approximations of reality. They are not reality. And so we always strongly encourage our engineers to go back to first principles, simplify your system, try to be able to predict the loads that you're getting in that complex FE model by hand. As one of the reasons we're building this branch software is because I want to create a piece of structural design software which thinks like, I call it a senior engineer would. It rationalizes the structures down to the basics and down to the way you might, rather than kind of masking reality with complexity.
Yes, Martha, please. I can repeat your question, or we can bring you the mic.
But the ingenuity of the craftsman on the floor. And I have a dual question. One is, do you find that, I'm sure you have retention on the floor, but do you find that you have young people coming in to want to be craftsmen like that? Because I have a view about what's happening in general. And secondly, do you feel that as things are changing, that craftsmanship can be replaced by robotic fabricators that can really try to understand, touch, and feel the material the same way that humans do right now on your shop floor?
Great question. Do you want to repeat it? It's good.
I think everyone heard it.
Yeah, everyone heard it. Okay. Yeah, I think to answer the first part of the question, how do you inspire future generations to want to have this deep connection to crafting a material and to not regard that as a job that is a menial one, but to regard it as a high calling? It's a challenge, and it comes to, I think, our philosophy, and it comes also to kind of, I think, our teaching environments and how we inspire students right from high school through university, and the ecosystems that surround that into thinking about what they want to do in their careers. We have in our shop master carpenters from Japan, from Germany, from Italy, from Canada, the US, all over the place. And each of those different cultures has a different approach to training and passing down the tradition of joinery or of carpentry. And you look in Japan, for example, the daiku, it was passed down for millennia, this tradition of the joints, some of which I showed today. And that is still highly regarded. And here, we are trying to certainly re-inspire that, but it can be a challenge. And then your second part of your question about can robots replace the human? No, it can't. First off, you're always going to need a human to run the robot. You're always going to need a human to think about, well, what clever way could I make that robot do that thing next? You're always going to need a human to clean up when the robot couldn't handle that little piece of wood that got cut off when it shouldn't have, and now it's stuck in the machine, right? There's all these things that just require the human touch. And sometimes humans can be more efficient than robots. And so I think the future really is this human-robot collaboration. We got a 6-axis robot at our shop. We use it all the time. But we don't use it to think for us. And we don't necessarily use it to limit what we can envision in terms of joinery. Many of the joints I showed today would not be possible on the latest Hundiger, CNC 6-axis robot. Can't mill them. And therefore, in many modern engineering, timber engineering companies, you can't build them, right? Because you want to make sure it's CNCable, but do you? And do you need to? So I think, continuing to ask those questions and continuing to keep the art of craftsmanship alive is incredibly important.
So you talked before about how one of the bigger barriers to the kind of work that you're looking at is the litigious nature of the industry right now. But beyond that, there's also the time and cost associated with going through developing these kinds of details, which would cause a lot of people to hesitate to try to go that route. Can you comment a little bit more on your experience with the time and the cost associated with it compared to using more standardized details? And then also, how do you navigate that conversation with the design team and the shareholders and people who are involved in the financial aspect who just want their things built?
Great question. It doesn't have to take more time or necessarily cost more. The project I showed in Barbados, we went from start of design April 1st to built structure end of August. If you can imagine, it's an incredibly short time window. Really what it takes is restructuring how we think about procuring our building structures. And so but with our company, because we're both the structural engineer of record and the builder, we can short circuit a lot of that, and we can take some of that risk and de-risk it for the owner. In fact, the owner is trusting in us to be able to make that happen for them. And some of that innovation actually helped us. It didn't hinder us from a schedule perspective. And so I think with more traditional clients, yes, that could be a challenge. But I certainly like to challenge, how we procure, or how our contracting environments are set up, and maybe by returning some more of the risk to people who control both design and construction, we can actually deliver our buildings faster, because we no longer have to go through the process of 100% DD, 100% CD, tender, design assist, value engineer, change it 3 times, and then go finally bid it and procure it. We can actually just have a target budget in mind and go design to that from the start, and actually reduce the amount of time it takes to deliver our structures.
Hi, Lucas. Awesome talk. Congratulations. That was really fantastic. I have a question, and I'd love to hear more about the visuals you showed us, because I think that really helped take us all on a journey with you. And in many ways, it's sort of approaching, you were letting the unseen be seen throughout a lot of that. What is driving the effort to produce those, show them, and what are you achieving across the range of people you're showing that to in terms of clients, the public, and what's driving that in terms of getting your message or some point across?
That's a great question. First, I need to give a big shout out to Shasan, one of our team members who's here today, who produced a lot of the animations that you saw today. Incredibly talented guy. And then, yes. And then secondly, I need to say, this is about the art of storytelling. So it goes back to, I was talking about interfaces between us as designers and builders, and between our minds and the things we're envisioning in our minds, and how we communicate them to people. I'm a strong believer in storytelling, and by telling the stories of our buildings and our structures and how they work, we can inspire them not only to be interested in the insides or the innards, as you mentioned, but also to want to do more. And so yes, it certainly helps us not only communicating how our buildings work, but also inspiring not only external clients, but also people inside our own company to think about, well, how did that structure actually get built? I ran a class on, I call it structural storyboarding. One of my side pet peeves is that our drawings now look like an X by Y grid of unrelated details, which I absolutely detest. Our structural drawings should be stories of how our buildings are going to go together. The people who read those drawings are the ones building them, and they don't want to use 3 or maybe 4 fingers in the set to try to figure out what's going on. And so, telling stories in our drawings, telling stories with our details is really, really important.
Hey, thank you so much for the right over here. Thank you so much for the presentation. Everything was really delightful to look at. I'd like to hear from you as the joints and the details that kind of emerge are understated or like quietly beautiful. Is there anything that drives the aesthetics other than sort of the form finding or the forces? Like, does the master carpenters from Japan versus master carpenters from Germany really impact like the sawtooth formation or the chamfers, or like to hear a little bit more about that?
I remember we had a debate with 3 master carpenters, all from Japan, about how one particular joint should go. Yes, it does impact things, for sure. I think there's no single right answer. But the things that impact our connection design are really beauty, efficiency, structural efficiency, and cost. If you break it down, those are the things that really kind of hone in. And if you can hit all 3 of those things, then you've kind of created something. You've reduced it to its absolute simplest form, and you've created something that can be worth putting in your building or worth celebrating.
Hi, Lucas. Thank you for your talk. I think I was wondering, like the part where you're talking about the project in Barbados and how it was kind of shipped from Vancouver over there, and I'm just wondering if there's ever like consideration of how like the life cycle and how like the transportation, like the carbon associated with transportation factor into like how you guys make design decisions, or has there ever been like an instance where you guys feel like you turned down a project because you felt like, maybe like not making it with more local materials might actually have a lower embodied carbon? Just kind of like how does that factor into your firm's like design philosophy?
That's a great question. I think shipping and transport carbon is quite interesting because it can be more carbon intensive to truck a product from one coast of North America to the other than it is to ship it on ocean freight from Europe to the East Coast, for example. In the case of the project in Barbados, air freight would have been, probably 10 times worse than what we ended up doing, which was ocean freight. But yes, I mean, it's a consideration, but generally, the way I look at it is our job as engineers is to use the materials we have responsibly, minimize the materials. I think we often, as structural engineers, over-design our structures, and that's become ingrained in our building codes and our approaches. And so, our biggest attempt to design sustainably is by designing efficiently. Clients are going to build the structures whether we're involved or not at the end of the day. In Barbados, for example, almost everything comes from off-island. And so, yeah, it's certainly a case by case.
Hi, I have a question. You talked about the initial stresses in the material dissipate over time. So how do you account for that in the joinery details? And does that change of forces in addition to environmental changes over time and seasonally affect your expected performance in those joinery?
Yeah, timber is a fascinating material because its structural capacity does change, both with the duration of the load, but also with the environment. So the relative humidity or the moisture content in the wood changes its capacity and compression perpendicular to grain, parallel to grain, et cetera. And so you have to consider all those things when you're designing. For example, if you put 2 pieces of timber end to end, and you press them into each other, what actually happens is at a microscopic level, if you imagine timber like a bunch of straws, right? The straws actually, they're all of different diameters. They actually press into each other, they slide by each other. And so you actually don't get the same compressive capacity that you would get if you put a steel plate in there. So there's all sorts of interesting kind of microscopic things to understand about how timber as a natural material works. It causes, not necessarily to over-design, but to understand, test it, truly understand, get with the latest research and understand how it behaves.
We only have time for a few more questions, so if you have one, either raise your hand or come up. Okay, yes, please.
All right. Thank you for this talk. I really enjoy, totally. I have to push a little bit outside of current talk, maybe, because I'm limited to the Earth, on Earth. I'm just wonder, based upon all the practice and our experience and knowledge we gain, and have you ever worked on any hybrid material using wood or steel or something that can we offer to our knowledge to the aerospace technologies? Recently the SpaceX continuously successful to launching the Super Booster and a Blue Origin. Obviously, they successfully successful. Can we offer anything that's something from us to their communities?
Good question. Of course, the earliest planes were built with wood. And the Aerospace Museum I showed actually was made out of wood because the founder of that company had built his own wooden airplane around 60 years ago and flown it. And yes, so of course we could use timber to fly. Should we, or is it practical is another question. There's some very interesting material advances happening with timber right now. You may have heard of superwood, this new product which is thermally adjusting and compressing wood to actually create this fiber lignin level bond between the fibers, and turning wood from something which is very weak perpendicular to grain into something which is actually quite strong, and turning the bending rupture modulus of timber into something in the range of 400 MPa. So it's like steel. And so yes, there are material advances happening. Wood as a natural material, is that the right thing to put into plane today? Well, certainly in some parts of the plane, maybe not the entirety, and certainly not rockets.
Here, great talk, thank you. Okay, my question is twofold. So with regards to branch specifically, I was hoping you could talk about like the relationship between maybe indexing, generation, and simulation for some of those joints, right? Because if you have a novel set of structures, how do you actually evaluate, almost every option, or is it just that you pick a few and you fly with it? And then the second part of that is, if you make a tool that is accessible to anyone, which it seems like what you're doing, right? Like the issue with procedural generation is that it leads to a high level of monotony, but that's not like how natural structures tend to evolve. And so like, what are you most excited about in your, like in Lucas's 10, 20, 30 year view? Like, what do you think you can do with it,
Good question. I like to think that computers will return to truly aiding us. Right now I look at it as computer-limited design. I think we're going to see a revolution in software which will greatly improve not only the speed at which we can investigate solutions, but also the breadth of solutions we can investigate in the first place. I talked about that a little bit earlier, but I think right now the computers tend to maybe constrain us more than they release us. And then to your question about joints, at the end of the day, you have to pick something and try it. You can't go and investigate, a million solutions. You don't have time and practice to do that. So you got to use your intuition. At the end of the day, the best optimization algorithm is the human brain, because it can do multi-objective optimization like nothing else. And so, you use the computer to give you the information to make the decision. Don't let the computer decide for you.
All right, and I think that's a wonderful point to end on. Please join me again in thanking Lucas.